In this week's lab, we are going to look at reactions and the factors that affect them. We're going to look at basically how things like temperature and concentration and the presence of a catalyst can affect the rate of a reaction, can speed it up accordingly. And we're going to look at reversible reactions, where the forward and reverse reactions occur at the same time. And we're going to see how this equilibrium that gets established can be shifted using Le Chatelier's principle. So we'll look at various factors that affect the position of this equilibrium. So over here I've got two test tubes, each with 10 milliliters of 0.1 molar hydrochloric acid. We're going to look at the effect of temperature on the rate of reaction. So we're going to add some sodium bicarbonate or baking soda to the samples of hydrochloric acid and see how quickly the carbon dioxide bubbles clear away. Now, we have a hot test tube and a cold test tube, so we're going to see the effect that temperature has on each of these solutions. All right, so if we look at our thermometer here, we can see that we are at a temperature. It might be a little hard to see here with this webcam, but I would say we're about 52 degrees Celsius, probably climbing a little bit by the time we get this thermometer taken out, or this test tube taken out. But we'll let this ice bath here also cool down. We can see what temperature that's going to be at. All right, now it seems to be cooling down to about, might be a little hard to see there, but right now it's about 6 degrees Celsius. Okay, so let's go ahead and put those in a test tube holder. Okay, so I have my two test tubes here. The one on the left is the hot one, that's about 53 degrees Celsius, and the one on the right is the one that dropped down to about 6 degrees in the ice bath. So let's go ahead and add a spatula tip full to each of them quickly. You should be able to see a clear difference in their levels of reactivity. So you can see, if you're having trouble seeing them, the one on the right is still going. It still has, you can see the cloudiness from the unreacted sodium bicarbonate and the bubbles that are still evolving from it. Whereas the one on the left is our hot water one. You can see that it's definitely cleared up a lot faster there. Okay, so if you're having trouble seeing that, let's hold that against the dark background of the of our bench top here, and hopefully that'll be a little bit easier to see. Okay, so you can see our test tube on the right still has bubbles evolving, okay, whereas our test tube on the left, which was in the hot water bath, cleared up much, much quicker. Alright, here we have 3 test tubes of hydrochloric acid, each with 10 milliliters, but the difference between them is the concentration of the hydrochloric acid. In our test tube on the left here, we have 1 molar hydrochloric acid. Okay, that means that for every liter of this solution, there's 1 mole of HCl dissolved in there. In our second test tube, we have 2 molar HCl, so double that concentration. And in our third test tube, we have 3 molar HCl, triple that concentration of our first one. Okay, so to each of these, I'm going to add some magnesium ribbon. I'm going to add a piece of magnesium ribbon, and I'm going to have a stopwatch running, so please make a note of the time at which each test tube clears. Okay, so once all of our magnesium has dissolved, you can make a note of that time. Alrighty, let's start with our 1 molar hydrochloric acid. I'm going to take a piece of magnesium ribbon and add it into our test tube and start our stopwatch. And go. Okay, you can see the hydrogen gas that's bubbling from there, that's being produced as the magnesium displaces the hydrogen in our hydrochloric acid. So keep an eye on that, and again, make a note of the time at which all of the magnesium has disappeared, and you have, basically all of your magnesium's been converted into magnesium chloride, and your hydrogen in your hydrochloric acid has been converted to hydrogen gas. So it's still bubbling, so make a note that, basically you're waiting for it to stop bubbling completely. A little trouble seeing that. Okay. Looks like that's just about done there. Alright, next up we have our 2 molar hydrochloric acid. So same thing, we'll go ahead and drop our magnesium in. We've got our magnesium ready here, and we'll start our stopwatch as soon as we do that. And go. Yeah, notice that the bubbling seems to be a little bit more vigorous here, right? So please note that rate and time are not the same thing. When the speed or rate of your reaction increases, the time it takes to finish should decrease. So be very wary of how you phrase your answer. So you can see already that you might want to rewind this and see at what point the magnesium disappeared, but you can see it's already all gone. So be wary of how you phrase your answer, whether you're talking about the speed or rate of the reaction versus the time it takes for the magnesium to disappear. Alright, and here's our third and final test tube of 3 molar hydrochloric acid. We're going to add our magnesium to that and get ready to start our stopwatch. And go. And notice this is the most vigorous yet. So again, the speed at which the reaction occurs, the vigor, or those bubbles appearing, so that effervescence, is not the same thing as the time it takes for it to disappear, which hopefully you should be made a note of there. Okay, and that's it for that one. In this part of the lab, we are going to take different catalysts, or things that could be catalysts at least, and add them to the decomposition of hydrogen peroxide. Now, if you recall from an earlier lab, hydrogen peroxide decomposes into water and oxygen gas, but this reaction is very, very slow. Now, we sped up the reaction last time using some potassium iodide, and so in this lab we're going to try a few other things to try and speed up this really slow reaction. So up here you can see I've got 5 test tubes. I've already added 2 milliliters of hydrogen peroxide to each of them. Okay, so if you want to have a little bit close-up look over there, there's our 5 test tubes, and it's kind of hard to see any bubbles forming. Right? I'll see if I can get you a closer look later on once we get these reactions started. The various catalysts or potential catalysts we're going to use today include manganese 4 oxide, commonly known as manganese dioxide. We have mossy zinc, which is basically just little chunks or granules of zinc. Over here we have the world's cutest potato. Potatoes are very versatile. They have, well, you can boil them, mash them, stick them in a stew. But they also contain catalase. Now, catalase is a protein that functions as an enzyme. Now, if you've taken a biology course before, you've probably learned about enzymes and learned that they are basically protein catalysts, right? They can catalyze reactions, speed them up, or carry out certain reactions. So catalase is one of these. So we're going to see the effect of catalase on hydrogen peroxide to see whether it happens to catalyze that particular reaction or not. Over here, of course, we have some boiled potatoes. Now, why are we using boiled potatoes as opposed to a regular potato? Well, boiling actually denatures catalysts. It denatures proteins in general. It causes the shape of the protein to change, and therefore it doesn't have the same physical properties, and in some cases chemical properties. So we're going to see whether the denaturing of the catalase protein in your potatoes stops it functioning as an enzyme, stops it functioning as a catalyst. Okay, so something to keep in mind when you see the results of this lab, okay, or this part of the lab. Alright, I've gone ahead and added a dark background here to our 5 test tubes, each with 2 milliliters of hydrogen peroxide. So hopefully that'll make things a little bit easier to see. And as I mentioned, I might take a close-up with my cell phone to give you some different footage here if it's a little bit hard to observe what's going on. Now, over here in our first test tube, we're going to use this as our reference or standard. So I'm basically not going to add anything to this. This has 2 milliliters of hydrogen peroxide, and you can kind of see what the effect is when we don't, when the reaction happens uncatalyzed. If you recall from the lab we did earlier on types of reactions, this is a very slow reaction. So even though technically this is decomposing, this is happening so slowly that you probably won't observe any bubbles of oxygen forming. It's almost impossible to notice.
Here's a close-up of our reference test tube or standard, just so you can see, the lack of evidence of decomposition here, just showing how slow this uncatalyzed reaction is. You can't really see any bubbles right now. So again, this is a good comparison for whether or not we have a catalyzed reaction. You'll see that when we do have a catalyzed reaction, there'll be a pretty stark difference in the number of bubbles and the speed at which they appear.
Okay. So to the second test tube over here, we're going to add a little bit of our manganese 4 oxide. Okay, so let's go ahead and add a tiny spatula tip full of that, and we'll get to observe some of that reaction.
Here's a replay of that addition of manganese 4 oxide, just a little bit closer up, so you can see definitely there's a significant difference here from our standard, our reference test tube. Okay, so all those bubbles you're seeing are actually bubbles of oxygen gas being produced by the decomposition of hydrogen peroxide into water and oxygen. Okay, so notice the vigorous bubbling that we observe here compared to our reference test tube.
All right, to this third test tube, we're going to add our mossy zinc. So again, just take a little piece of this zinc. Probably take this little chunk here. I don't know if you guys can see that very well, but there's a little chunk of that zinc. We're going to add that to test tube number 3. And there we go. Here is a potato. I'm going to cut out a chunk of this potato and add it to test tube number 4. So I'll just use a spatula here. That should probably be sufficient to get the job done. So if you want to see that there, just take out a little chunk of that. There we go. So we'll go ahead and add that to test tube number 4.
Yeah, there we go. You should be able to see the bubbles coming off of our chunk of potato. Okay, so hopefully from this angle you should be able to see a stream of bubbles coming off of our potato. Okay, so please make a note of that. Feel free to make a note of the rate at which they're coming off if you want to compare them. I believe one of the questions in this section of the lab asks you to compare, to decide which is the best catalyst we have. So determining how quickly the bubbles are coming off of our potato might be something to keep in mind when you're comparing the different the effectiveness of the different catalysts.
All right, so here we've got our can of potatoes. So again, these have been pre-boiled before they were canned. So you can see we've got our slices of potato here. I'm going to go ahead and cut out a chunk of one of these with a spatula and add it to test tube number 5. And we'll go ahead and observe, what there is to observe. Yeah, I'm very careful here to use a fresh spatula. Don't want to use the same one I used for the potato in case any of the fresh enzymes on our fresh potato get in here onto our boiled potato. So here's just the boiled potato added to our hydrogen peroxide there. Okay. And I'll get a close-up of that for you guys to observe.
All right, so you probably notice some things floating around in there. Those are just flakes of boiled potato. You can tell they're not oxygen because oxygen gas would start. Those bubbles of oxygen gas would be rising to the surface of our hydrogen peroxide solution. You can see that that's not the case. All right, so I think there's a few bubbles at the top there that are staying stationary. Those are probably just air that got trapped when the potato chunk was dropped in. I'm going to shake this up to kind of get rid of those bubbles, hopefully. Just disrupt those. I guess I'm making more bubbles there. Let's disrupt those. There we go. Still a bubble or two that's left on the surface, but again, the fact that those bubbles aren't rising and dissipating tells you that's not oxygen. That's just trapped air. So again, you can see the little bits of flakes in there. Those are flakes of potato, not actual oxygen gas. Okay, if they were bubbles of oxygen gas, they'd be rising up to the surface. Okay, they're just sinking to the bottom because they're potatoes.
And I just wanted to point out this little difference between boiled potatoes, or this fresh potato over here, and a boiled potato over here on the right. Again, if you notice that difference in catalytic activity between them, again, catalase, which is a protein found in potatoes, is an enzyme, which is a protein catalyst, right? It acts as a catalyst, and I could let you interpret the evidence you see in this lab. But the key thing to realize with our boiled potato and why any enzymes present in your boiled potato don't work, it's because proteins get denatured when you heat them up. They essentially change their shape, and the shape of a protein is very important for its function. Okay, so it stops behaving the way it normally does. Its physical and chemical properties change when you heat it up, and it changes its shape. So the catalase that's present in a boiled potato no longer functions as catalase. So that's something to keep in mind. In this last part of the lab, we're going to look at one equilibrium in particular. We're going to take iron 3 plus ions from our iron 3 nitrate here, okay, also commonly known as ferric nitrate. We're going to react it with potassium thiocyanate. So the thiocyanate ions in our solution are going to form a complex with the iron 3 plus ions. Now, we've seen this reaction multiple times before. If you recall, you'll get this sort of dark reddish color from the complex that's formed. Okay? Now, this dark red complex exists in equilibrium with the original ions separate here. So we're going to see Le Chatelier's principle by playing around with this equilibrium. We're going to make a mixture of these two compounds, right? And start off with 6 test tubes off that mixture. Okay, now one of these is going to be a reference. We'll just add water to it. But we're going to add various things to our other test tubes, or in the case of the last two test tubes, we're going to change their temperature. And we're going to see the effect of these different changes to the equilibrium on the equilibrium. All right, I've added 10 milliliters of 0.01 molar iron 3 nitrate. I measured at 10 milliliters in a graduated cylinder and went ahead and already poured it into this to this beaker here. You can see it's this kind of yellowish solution. You may recognize it again from a couple of labs ago. Over here, I've measured out 10 milliliters of 0.01 molar potassium thiocyanate. Again, notice it's a clear, colorless solution. Oops, see if I can. There we go. That should make it a little bit easier to see that color there. Now, if you observe, when I add one to the other, notice that rich red color that we observe. Okay, and so and we have this nice red, deep red solution, kind of a blood red, or like a wine red, I guess. That's the iron thiocyanate complex that we make. Okay, so that's what we're going to add to each of our 6 test tubes, and we'll go from there. All right, you can see here that I've added about 3 milliliters of the solution of our equilibrium mixture to our 6 test tubes. Now, to our first one over here on the left, I'm going to add 10 drops of just plain distilled water here. And we're going to use that as our reference test tube. And there we go. Alright, so we have 10 drops of water there. Just going to shake that up a little bit. Slightly dilute our solution down, but you can see that, and increase our volume obviously as well. But make a note of the color that we've got here. I'll leave this up so then we can compare colors for all of our subsequent test tubes that we're going to add different chemicals to. Alright, so over at test tube number 2, I'm going to add 10 drops of 1 molar iron 3 nitrate. Okay, so the thing to observe here, of course, with our iron 3 nitrate, first of all, notice that this is 1 molar iron 3 nitrate, so it's much more concentrated than the solution we started off with. So the key thing here is that we're adding iron 3 plus ions to this. So think about how that might affect the equilibrium between our individual ions of iron 3 plus and thiocyanate on the left, on the reactant side, and our iron thiocyanate complex on the product side of this equilibrium. Alright, so let's go ahead and add our 10 drops of solution of our iron 3 plus solution to this. Okay, so hopefully you've noticed a key, especially if I shake this up, there we go, it's nice and evenly mixed. You should be able to notice a key difference between test tube number 2 that we added our iron 3 nitrate ions to, and test tube number 1, which was our reference. Okay, so please make a note of that difference. Now, to test tube number 3, we're going to do something similar. We're going to add 1 molar thiocyanate, potassium thiocyanate solution. So again, the idea here is we're adding the reactant thiocyanate. Okay, so think about how this might affect your equilibrium. Okay, and give it a good shake, and once again, you can kind of compare its color to our reference test tube, and again, you should be able to see a clear difference between these two test tubes. Okay, so now for test tube number 4, we're going to take a concentrated solution of hydrochloric acid. All right, so this is 3 molar HCl. Hydrochloric acid is going to react with our Fe3 plus ions in solution and form an iron chloride complex, which basically prevents the iron ions from reacting with thiocyanate. So what effectively this is going to do is this is going to remove iron 3 plus, okay, that reactant Fe3 plus from the solution. Okay, so think about the effect this is going to have on your equilibrium accordingly. So we're going to go ahead and add this to test tube number 4. That's this test tube over here. Okay. Okay. So I'll go ahead and shake that up just to make sure that everything's well mixed. Okay. And again, you should be able, hopefully, to see the difference between our test tube number 4 and our reference test tube number 1. There should be a pretty discernible difference between the two. Okay, so please make a note of that difference and account for that difference. Why did we see the difference that we do? You know, which way has this equilibrium shifted? All right, for the last part of this section and the lab in general, we're going to take test tubes 5 and 6. We're going to put them into an ice water bath and a hot water bath, respectively, and see how that affects our equilibrium. All right, so accordingly, you'll see that one of these will shift towards the reactant side, the other shifts to the product side. You should be able to tell pretty easily based on the color change, right? And describe that accordingly to explain why. You can tell one's the reactant and one's the product. The reason for this shift is that heat could be treated as either a reactant or a product. Okay, so remember, for an endothermic reaction, heat's absorbed by the reaction, right? So you could treat heat as a reactant in that respect. Likewise, for an exothermic reaction, heat is given out. Okay, so heat's a product, in other words. So for our equilibrium, heat's going to be on one side of the equation. So if you're looking at that forward reaction, it's either going to be endothermic or exothermic. So heat's going to be a reactant or product accordingly. And the opposite, of course, for the reverse reaction. So for the last part of this lab, we're going to figure out on what side of the equation we're going to write down heat. So just look at the way this equilibrium shifts in these last two test tubes once we put them in our hot and cold baths respectively, and you're going to observe whether heat, how adding heat changes the equilibrium and how removing heat changes the equilibrium. Okay, and that'll tell you whether heat's on the reactant side or the product side. Alright, as you can see, I've had my test tube number 5 over here cooling down in an ice bath. Okay, and over here test tube number 6 heating up in our hot water bath. So they've been heating in there sitting in their respective baths for quite a bit of time. And so yeah, hopefully we can observe a little bit of a difference here between them. So let's take the two of those out.
Okay, so here I've gotten our two test tubes. So test tube 5 on the left, that was in the ice bath. Test tube 6 on the right, that was in the hot water bath. And hopefully you should be able to clearly see the difference between them. It's a little bit more subtle than some of our other test tubes, but again, you should be able to tell a difference here and tell which one shifted to the reactant side and which one shifted to the product side. So even though one of our test tubes hasn't gotten as dark as some of the other test tubes, I will point out that our reactant, that one of our reactants at least, iron 3 nitrate, is that sort of yellowish color, and our product, the iron thiocyanate complex, is a deep red color. So based on that, you should be able to figure out what's going on in these two test tubes.
Alright, so here are all 6 of our test tubes shown once again. And if you want to compare with our reference, you can see, again, all of how each of our test tubes have changed color accordingly. And again, with the last two, it's a little subtle, in terms of that difference. But hopefully, lined up next to the reference and perhaps one of the other test tubes, you should be able to figure out what's happened in test tubes 5 and 6.
All right, so let's just briefly walk through the lab report together. I think part A should be pretty straightforward. Please note all of the questions in this lab report have to do with interpreting your observations, your results. So please answer all of the questions that are tied into this lab report. Okay, none of them are just practice problems. They're all relevant to the lab. For part A2, please note that we only measured the total time. We used a stopwatch. So even though we have columns here that say initial time and final time, that would be if you had a running clock that you were using. So really you can just ignore these two columns here. Just leave those blank. Only record the time from the stopwatch in this column. Okay. When you're framing your answer, please be careful. I mentioned this in the video, but be careful about the difference between time versus rate or speed. Okay, those are not the same thing, and how you describe your answer gets kind of flipped depending on which word you use. So be careful of what word you use in your answer. For example, if a reaction speeds up, the rate is faster. The time is shorter, right? It takes less time for the reaction to happen if it's a faster reaction with a higher rate. And vice versa, obviously. So be careful about how you frame your answer. I'll accept either way you frame it, whether you're talking in terms of speed or rate, or if you mention time. Just be careful, because I've had students who use one and mean the other. With questions 3 and 4, I kind of talked already about question 4 in terms of the difference between a fresh and boiled potato. I probably went into a little bit more detail than I should have, but again, this is just for the benefit of those of you who may not have come across catalysts or proteins and things like that, enzymes, especially if you haven't taken a biology class before. With question 3, though, I want to draw your attention to the way you should frame your answer. There's actually 2 parts to this question, and I think where a lot of students go wrong is that they only answer one part of the question. Okay, so the question is, how does a catalyst change the rate of a reaction without affecting its equilibrium? Okay, so I think most students usually answer the change the rate of the reaction part. And by that I mean, don't just say that it speeds up the reaction. Explain how does it speed up the reaction. But you need to address that second half of that question. Why doesn't a catalyst change the equilibrium position? Okay, now there are multiple ways you could frame this, but typically I would recommend looking at both the forward and the reverse reaction for this equilibrium. Okay, so think about the effect of usually, like when you're thinking about how your catalyst changes the rate of a reaction, most people think of just the forward reaction, but also think about what's happening to that reverse reaction as well. Okay, and that should answer that second half of that equation, of that question. All right, and let's see, for B1, I mentioned this in the video, but again, please note that the final condition here, after you've heated up your test tube, is your starting point, your initial right before you add water. So whatever observation you have here also goes over here. Okay. Yeah, and I think for both B1 and B2, please note that when they talk about reactants and products, and really this applies to part C as well, wherever we mentioned reactants and products. That's the way it's defined in the pre-lab or in the directions. So if you go back to the directions, okay, you can see that they give us the equation of what's going on. All right, so here in B1, here's our copper 2 sulfate pentahydrate. That's defined as our reactant over here. Okay, and our anhydrate is the product as this equilibrium is defined, as this reversible reaction is defined. In the case of part B2, please note that here our copper ions and hydroxide ions are the reactants, and our product is the copper 2 hydroxide. Okay, with part C, our iron 3 ions and our thiocyanate ions are reactants, and the red iron thiocyanate complex is our product. So again, keep that in mind when you're answering the questions for part C. All right, so I think most of that should be relatively straightforward. When we get to that last part, question 14 over here, all you've got to do here is you just have to add heat. If heat is a reactant, you would just add heat plus on the left-hand side. It's just saying heat plus iron 3 plus thiocyanate gives us that complex. Or if you determine that heat is a product, then you would put heat on the right-hand side of the equation. You just have iron thiocyanate complex plus heat. You would write that over here. Okay, so that's it for this lab. If you have any questions, just let me know, and good luck.